find a good time, please, to ask the questions. So the topic of today is some interesting and new ways to do computing on for digital computing with superconducting computing using Josephson junctions, and the reasons and some reasons of why that method of computing is a better fit for that technology compared to traditional CMOS. So, see, does this? Okay. So being a DOE National Laboratory, we get to talk to a lot of interesting scientists, and they have some really cool problems. There's a class of scientists that use superconducting sensors, and I'm sort of including quantum here, but you can include it in this category because it shares many of these characteristics. But we also have many other scientists who work on particle detectors, for example, and where the sensors themselves are in cryogenic temperatures, in the millikelvin in the very, very cold temperatures, just a few millikelvin. And there, what's happening predominantly today is what you see here on the left, where you basically get the output of the sensor directly, whether that's a current most of the time, and sort of take that through multiple stages of amplification with squids a lot, so different temperatures, different squid, and you export that analog information, the current information, oftentimes in room temperature where all the processing happens. We want to move from that on the left to what you see on the right, which I think a lot of you will probably be resonating with, because I mean, again, I'm mentioning quantum because it sort of relates, but it's a similar thing. We want to be able to do cold processing, to do digital computing at the 4 Kelvin for these sensors. And why we want to do this? Because then we can extract that information that the sensor gives us, like a particle coming in, with less, with fewer cables and more reliably if we do that digitally rather than in analog, as well as be able to do some pre-processing. So be able to discard a lot of information that the sensor gives us so that we can export only what could be interesting to room temperature. And a lot of that is to save power, reliability, and cabling. There are a few applications in this domain. One that I think is an interesting example, this is not my slide, is superconducting magnets, which are one way to do particle detection. So superconducting magnets, one of the problems that they have is what they call quenching, which is basically that the magnet itself enters a state that the voltages keep increasing until something bad like a meltdown happens. You can see here from the left that you can see that the currents keep steadily increasing, and that is sort of the precursor of that quench event that I was talking about. And you can see some on the bottom left, some readouts from voltages that you sort of see this step up behavior, but not in one nice clean line. So there, the question is, can we detect the precursors of these events? Could be with AI. It doesn't have to be that complicated in many cases, though. And can we provide a rapid response? Because depending on the type of the superconducting magnet, the latency of making a decision, okay, shut down the magnet, something bad is going to happen, can be important. So in those cases, we're definitely even more motivated to make this decision at the cryogenic temperatures. So this is just one example of why we are interested in digital computing for superconducting. Of course, there's also the HPC side of it. We have some kernels that are really compute intensive, and this is a promising technology to replace CMOS. I'm not getting into that right now. I just gave you an example. But then when we're looking into digital computing using Josephson junctions, predominantly that's RSFQ, not only, of course, there's a lot of variants and alternatives, but for many of these technologies, area is a primary constraint because device density is way behind modern CMOS. So area is a primary design constraint, how much we can fit, and of course that also means that memory capacity is a primary constraint. That has many implications. I just show you here one example from 2019, a demonstrated chip, 48 gigahertz, 8-bit multiplier, but only one of those was able to fit in one chip. So only one 8-bit multiplier. That's clearly not enough. Like we talk about HPC applications, that's a big constraint. But even if we talk about the magnets, the sensors that I was talking about, we have to, instead of one multiplier, be able to fit all the logic that I sort of alluded to, like AI detection or responses and all that, in the equivalent area. So areas is a big deal. There's also cabling, that's a big deal. And there's lots to say about there. What I thought was interesting, though, that's as what I was showing, is there are papers recently that try to use cryogenic photonics, and I'm showing you a graph of one of them, 2012 from UC Santa Barbara, where they show the sort of the state of the art in their work. In other words, what their work was able to achieve in terms of bandwidth. And notice that the bandwidths are small. So we're going from a high compute capacity technology like RSFQ and alternatives where the clock frequencies are high. So the multiplier, for example, runs at 48 gigahertz. And the cabling from there outside is low bandwidth, much lower bandwidth. So that creates a lot of design choices that we have to make, but also notice that the bandwidth increases as the reliability decreases. And that's something I'll come back to towards the end of this talk, but that sort of motivates us to operate at a lower reliability envelope to be able to use higher bandwidths. And then the third bullet has to do with circuit reliability under harsh environments. What I mean by harsh environments, that can be many things. It could be thermal noise, it could be external factors, it could be just noise in the current distribution network, anything that can make the circuit less unreliable. I'll allude to that sort of towards the end because it's sort of ongoing work or work that we'd like to get to kickstart. So with that motivation, we're moving into temporal computing, which is sort of how my involvement increased a lot in this technology, and that was mostly on the project that I'm showing you here. So it was between us and UC Santa Barbara, funded by AARO. You see a lot of good people who did a lot of the work that I'm going to talk about, as well as other work that I don't have time for. We went for 3 years. It was a good project, and we sort of started with this. Some of the motivations that I talked about. We didn't really focus on magnets or sensors at the time, but we definitely focused on area and a little bit on reliability. And there, one of the first things we did is we tried to move away from binary. So binary uses multiple parallel wires to represent numbers, at least typically. It uses gates that are some cases complicated depending on the operation. Like multiplication is expensive in binary. We saw that example before from that other paper. So we want to change how we do compute to alleviate a lot of that. So in other words, we're changing the architecture of the circuit to fix some of the problems that the device technology gives us, area being primarily that. So the way we did temporal computing here, so that basically means that when we talk about temporal computing, it's the time that something happens that encodes information. It's not that how many pulses you observe, for example, in RSFQ, it's when something happens. And in the example of race logic, which was previously proposed for CMOS, we adapted it in many ways to RSFQ, is basically the idea is, so we take time, that's the time axis you see in this case, in this slide is left to right. We divide time into epochs. Epochs repeat, so basically between epochs, all values reset because we have to reset the values, go back to 0 every now and then. So time is divided into epochs, and then epochs internally are divided into time slots. You can think of better names, sure, but time slots. The key though is that these time slots, each time slot is assigned to a value, a numerical value. So then when we going back to RSFQ pulses, in this case, RSFQ pulses is the event that I was talking about. So with this encoding, it's the time of arrival of a pulse. It's the time of arrival, again, that tells us the information. So if we observe a pulse within time slot 1, that tells us that that pulse is representing value 1. Whereas if we observe a pulse at time slot 4, it's representing the value 4. So we can broaden our representation range. So here I'm showing you 0 to 4. It could be 0 to 50. I can still do 0 to 50 with one wire, just like I could do 0 to 4. The problem is that now, because I'm still using one wire, it's great for area, but the more values I can have inside my epoch, I just have to wait longer. So it's costing me in time, and that's a trade-off that we're going to quantify in a few slides. But that's the basic idea of race logic. Now, based on that information, we also adapted how we do compute, because with that representation, some operations are really easy that were difficult in binary, but also unfortunately vice versa, and that's part of the stuff that I'm going to talk about later, how we dealt with that. But one example of something that is really easy is the min function. So the min function has two inputs, could be more, but in the simple case, two inputs, and it picks the smallest one. In the temporal domain, that is very easy because the smallest of the two is the first one that arrives. So the min function is what we call the first arrival gate, because of the two inputs, the first arrival is the first pulse that arrives. So you can see WRSPI's waveform here. So you have the two inputs at the top. You have a reset signal, in this case periodic. When the first one arrives, the first input arrives, we get an output pulse, because that's the minimum value, the output, the value of the minimum input, vice versa. And then this is a state machine, fairly simple. It's basically as soon as it observes a pulse, it is going to ignore any further ones until reset. Fairly simple. What was nice about the gates that we talked about, talk about here, this and the next ones, is that we can construct them out of cells, like standard cells that we find already in RSFQ libraries, like the SUNY library. In this case, it's a flip-flop with its clock input repurposed, but just for the sake of time, that's I think that just for the sake of time, I think that's enough of that. And then the corollary of that is the max function. So of two inputs, the last one that arrives is the maximum value of the two. See from its WRSPIs, two inputs, the last one that arrives produces an output. Likewise, there's a state machine that remembers, hey, I actually saw an input. Now I'm waiting for the other one. And these state machines show you that basically these gates need to have some memory inside them. They need to remember what they saw, and because they need to act accordingly for the next inputs. And that was one of the big changes we had to make to adapt race logic from CMOS to RSFQ. But these gates are also not clocked. So if you look at RSFQ binary gates, at least today, a lot of the work shows that every gate is clocked. There are many variations that don't, each with their different trade-offs, but this is one case, one example of a library or a logic family that does not clock every logic gate. The min and the max are not clocked. And likewise, we have some other gates, like the inhibit gate has a data input, control input, and if we have a pulse on the control input, it's going to suppress a pulse at the data input. So we use that for data propagation, for example. Likewise, there's a state machine and this one is actually pretty easy to. It's just one cell. It's just the inverter cell from the SUNY library that makes this possible. So going back to what I said earlier, the race logic makes min and max computations very easy. You saw it's only one gate, and that has good implications for some applications. So one of those applications is hyperdimensional computing. I'm not showing you the whole system here. I'm just showing you the key. One of the expensive parts of hyperdimensional computing is when you have vectors for every class that's being remembered, and that could be many, many vectors, could be tens, could be hundreds. When a query vector comes in, that query vector is compared how similar it is to every stored vector. But then the outputs of each of these comparisons is basically a number. It's like a similarity score. And there's a comparator at the end that picks the most similar. And that comparator is expensive. Like think of many, tens or hundreds of these class vectors. So these rows that I'm showing you here, you can think of log vectors of the end. This is one of the problems scaling up hyperdimensional computing. And one of the things we did is replace this comparator with so basically encode the similarity in race logic, so that then we can make the mean comparison that much more cheaply than we would do in binary, and that made hyperdimensional computing scale much better than it did. We have some power here. I'll move on. Okay. So, as I said earlier, some operations are much more efficient in race logic. Min and max are prime examples, but there are others that are in the form that I already presented. Race logic are much more complicated. So, for instance, one of them is multiplication. So, if you have a race logic value, an input, that in this case is the number 2, and you want to multiply it with the number 2 again, so 2 by 2 equals 4, we know that the output should be 4. But to construct a circuit that does that, that takes two race logic inputs and produces a race logic output, yeah, we can do it, but it's an expensive circuit. And that was one of the steps that we had to deal with, and that led us to USFQ, which builds on this race logic logic that we talked about, but combines it with pulse trains. So let me explain. If we take so far what I presented is what I'm showing here. So this is race logic where there's an epoch, there are time slots, each time slot is assigned to a value. But what I didn't stress, in this previous example, for simplicity, is that here each value is an integer. It works, it's great. But to make the multiplication case easier, and you'll see why, one of the modifications we did to this representation is we changed the representation to one of two ways. You can have a unipolar representation where unipolar means from 0 to 1, and then the number of time slots in an epoch tells you basically how many floating point numbers you have in that 0 to 1 range. So here we have 8 time slots. So we have the numbers from 0 to 1 that's shown here, like 0.125 and so on. So that's the unipolar case where it's 0 to 1, but then you have also the bipolar case, which is -1 to 1. And likewise, in that range, the number of time slots determines how many floating point numbers you have in between. So we've modified race logic by modifying the ranges that they represent. So that's one of the two operand types that we're going to be working with. The other operand type we're going to be working with are pulse trains. And pulse trains are not about when something happens. They're about how many events I observe. So you can have pulse trains in the unipolar or the bipolar case. I'm showing you here the unipolar case where I have 8 time slots, and in the top case, in the top row, I have a pulse in every time slot that I could have a pulse in. And that tells me that that operand represents the maximum number of the range, which in this case is 1. On the second row, I have half the number of pulses, so half the maximum number, so 0.5, and likewise, the last row is a quarter of the number, so 0.25. So again, this is about how many pulses. It's not about when they come. Of course, they still have to come, within the epoch. They still have an epoch, but it's about how many. And I'm back. Sorry, my headset will turn off if nobody speaks within 20 minutes or something. So it doesn't like me going on a monologue. All right. So yeah, so these are pulse train operands. Now, if we combine the two, now we've made multiplication much cheaper. So here I'm showing you such an example where one of the operands of the multiplication is a pulse train. That's operand A. And in this example, it has half the number of pulses, so it represents half the maximum number. So in this case, it's 0.5 is what I showed you before. And then we have the second operand, which is a race logic operand. And here, because it's a race logic operand, we only have one pulse. And in this case, it's a value of 0.25 because that one pulse drives in time slot 0.25. The key to making this work is we're going to use the race logic operand to suppress any other pulse train operand input. So in other words, every pulse that comes from this first operand, the pulse train operand, will be propagated to the output until the race logic operand arrives. And that will suppress any further other output pulses. And if we do that, the output is the multiplication of these two in a pulse train format. So in this case, it's 0.125. In this other example, where just the values are different, the multiplication output is 0.375. And why did we do all this? Well, because now we can multiply two numbers, a pulse train and a race logic number. In the unipolar case, which is what I showed you, we can do that with only one cell, an NDRO cell. So now we've made multiplication so much cheaper than it used to be. Even in the bipolar case, which I didn't show you, but it's the same logic, we can multiply with four cells, two NDROs, one merger, one inverter. And the whole thing and multiplication now just becomes so much cheaper. I promised you to quantify this trade-off, and here it is. Here we are comparing a binary multiplier with a unary multiplier. Unary is what I showed you before. That's U SFQ. And here we have bits on the x-axis, so basically the bit width of the operands. And in this case, the y-axis is latency because you see the label here. Now, as the binary multiplier has operands that have more bits, it does become a little slower because the critical path, prolongs, so the frequency drops. But and I didn't say the y-axis is logarithmic, so pay attention to that. So the binary multiplier does become slower, but it's not a dramatic effect. The unary multiplier becomes a lot slower because, as I said earlier, if I increase my numerical range, now I have to wait longer. So in other words, an epoch, if I compare an epoch for a numerical range of 0 to 3 versus 0 to 8, 0 to 8 is twice as long. So the whole circuit, because we have to wait for every epoch to end, now runs twice as slow. So it's this trade-off that we're quantifying here. But if we are to take 8 bits as an example, which is a good representative bit width for a multiplier, it also points to the example that I showed you earlier from ISSCC. So in this case, the unary multiplier is 6 times slower. Okay, so it's slower, great. But now if we compare the area, because we can multiply in unary in USFP with 50 JJs, regardless of bit width, the binary multiplier compared to that is huge. So the binary multiplier, or rather, like to match this, the unary multiplier is 370 times smaller than the binary multiplier, and it's of course 6 times slower. So it's a really good area trade-off. And building on this concept, okay, so we're talking about multiply. We can add the accumulate part, so the add part, we have different ways of doing it, but at a broad level, by basically merging the outputs of all these multipliers. We can do this in the cheap way, which is basically a counting network that's shown here, which is basically use merger cells. That works, but some pulses can get lost. So that can have a numerical effect, but it's not a huge one. Or we can have a more safe cell. We did all these designs in our papers, but the concept is the same. We basically have operands at every multiplier. One operand is race logic, the other is a pulse stream or a pulse train. You have these multipliers in parallel. All of them feed into some sort of way to merge them. In this case, it's a counting network, and you get one output. That's a pulse train. And then, we've done other work on top of that converts from pulse train to race logic, and so you can redo this loop at the next steps of the circuit. Not going to get into that here. just for the time, but all I can say is because now we represent pulse trains, I'm sorry, we represent values in the temporal domain, like in race logic. We adapted some of the cells that we often find in circuits. So like we designed this memory cell that basically accepts a pulse at one epoch and releases that pulse in the next epoch at the same time slot. So it sort of delays a temporal value, a temporal pulse in race logic by one epoch. And that's an interesting one. But then building on this multiply add circuit, now we've designed some interesting circuits with it. I'm showing you two here. One of them is a finite impulse response filter, an FIR filter, where you can see at the high level view of the circuit on the bottom left. It's a bunch of multiply adds, which is why it's a good fit to what we're talking about here. So the multipliers are, oh yeah, and this top diagram is the actual circuit at a high level view of it. So we have a multiplier bank that corresponds to the multipliers of the FIR. We have this counting network that's the adder, corresponds to the adder of the FIR. We have these memory cells that are used to input the coefficients at the right times. They delay the coefficients by the appropriate times. And then we have the coefficients that actually come as inputs, and they're stored in these NDA rows. And that was actually one of the earlier circuits that we did. Yeah, here's the catch phrase. It's resilient to errors. We've quantified that to some degree, and then depending on the numerical range, it can be 28 or 98% fewer JJs. But then what we did after that was also quite interesting is we took this idea and moved it into a convolutional neural network where now we have processing elements that are made up from these multiply adds and other parts, of course, that I just talked about. The interesting part has to do with the bit width, because the shorter the bit width, the faster the race logic and USQ circuits become, while they are also small. So small bit width, narrow bit width is a good thing for USQ. In the context of a CNN, what we're comparing here is the error efficiency. So basically throughput of operations divided by the number of JJ. So it's an area efficiency metric. So you have binary at the very end here on the left, and then you have USFQ with different bit widths. You see 4 bits is actually, it does well. It does, about 50 times better than binary, but it's also not very accurate. 6 was doing pretty well. 8 was doing great. We sort of settled as a good compromise. This 4,8 basically means 4 bits for the inner layers, 8 bits for the outer layers. And if we do that, it's at 10 to 20x better, depending on the benchmark in terms of area efficiency. Okay. We're about to not entirely shift gears, but to some degree. So I'm just going to pause if there are any questions here.
So I have one question about this circuit. So how resilient it is to jitter of the circuit or the bias variations?
Yeah, so jitter was not of the issues. So basically what jitter does, it prolongs the duration of a time slot. Because what happens is, think of a circuit like an abstract circuit. If a pulse comes in representing value 2, and you don't want the circuit to change its value, the pulse is going to go through some cells, so it's going to get delayed on the output of the circuit. So you want that pulse to be able to exit at the same time slot it entered, if that's the intended operation. So that determines the length of the time slot, and then jitter on top of that prolongs that time slot, so that even with the presence of jitter, that can still happen. Now there are games you can play with that. We can do wave pipelining. We can change the notion of epoch as the pulse propagates, and that does work. In some cases, we can also reset the epoch depending on the size of the circuit. Yeah, if that answers your question more or less.
Yeah, also about the parameter variation over the chip. So if you have pipeline data flow lines, different flow lines, then parameter variation can change the delay on each line a little bit. And how does that just reduce the frequency, or you need to have some other sort of the zero skew clocking, or in a larger scale to make it go through at the same time?
Yeah, it's similar to the jitter effect more or less. So one thing I didn't stress, let me go back to like here. When I talked about that there are epochs, that means that some cells have to receive a periodic pulse that represents that now we have a new epoch. It's sort of a reset. And if you notice, the first arrival cell has a reset. So there's still some sort of synchronous signal. It just goes to way fewer cells. So if we talk about timing variations, we're now like, for instance, here, actually, let me go here. So we have two inputs and they don't arrive exactly at the same time, but I still want them to represent the same number. That means, like before, the time slot has to be longer to accommodate that, which means that the epoch has to be longer to accommodate all the time slots, which sort of means that the frequency is reduced. I mean, I don't call it clock frequency because it's not a clock exactly, but the circuit operates slower. It
Okay.
graduates fewer results per time. Yeah.
So the throughput basically drops in that case.
Yeah, the throughput basically drops. Yeah, exactly.
Okay. Okay.
Yeah,
Thank you.
these are effects we studied to some degree in some of our papers, but we didn't have um, good, for example, jitter numbers from actual production chips that we can feed into our models. So maybe that's a point we can collaborate in, yeah, or something.
Yes. Yes.
Likewise in binary jitter, or these effects would reduce the clock frequency. So it's kind of at a high level, kind of the same thing. Okay, where was I? Okay, here. All right, and then um, we're building different. How should I phrase this? Okay, so building on this temporal computing idea, we talk about the compute part. We also wanted to look into the data movement part because we didn't want to build, very efficient programming elements that operate temporally. Then you have like 1,000 of them, but you have a traditional binary knock where every programming element now has to translate temporal to binary, take it through the network, and then binary to temporal, and because that would eliminate many of the benefits that I was talking about. What's interesting about on-chip network design in this technology is that the trade-offs are different. Some of the trade-offs are different compared to CMOS. So like in this technology, buffers, because they're memory, are much more expensive relative to CMOS. So we want to avoid buffers as much as possible. And on the other hand, the dynamic energy to traverse wires is small. Um, again, relative to CMOS. So how could we adapt a non-chip network design for these different trade-offs and keep the temporal nature of it? So we came up with this temporal network. It's a race logic. It's packet switched on-chip network. What I'm showing you here is the packet format. And the packet format in the simplest form, like here, you have a control part, like the header, basically, and then you have a payload. The payload is a series of pulses. You can interpret them binary, pulse trains, or race logic. Just a bunch of pulses that have to follow each other to go somewhere. The header is where race logic comes in. The header encodes where the packet is going, but it does so using race logic. So in this case, I'm showing you a network with 4 destinations, so it's a small network. And in this case, the packet wants to go to destination number 3 because the pulse appears in time slot number 3. It's race logic. This T star, you can ignore it. We have a little bit extra time to give the routing logic some time to act because there's no buffering in this network. And this is what the router looks like. The control path is in red, so routing logic and conflict detection, which is also part of routing logic. It basically detects if two packets want to go to the same output and then feeds that control information to the routing logic. And the data path is in gray. You have shift registers, but there's no buffers in the sense that there's no buffers that where packets can hold and wait. These shift registers are shallow. They're not a whole packet length. They're just there to delay the packet to give time to the conflict detection to do some of its work. And then you have the data crossbar. This uses deflection flow control because we want to avoid buffers. So two packets going to the same output, one of them will get that output, the other will go somewhere else. Well, somewhere else. In this case, there's only one other output to go to. So that's the router, that's the routing logic, and I'm only showing you that to show that it's not huge. We don't have to go into the details. It's a handful of cells. And then we have, okay, so we built a 2x2 router with this idea. How do we build a network? Well, we can build topologies based on these 2x2s. So here I'm building a 4x4 network based on these 2x2s by the butterfly topology, where you see here there's two columns of 2x2s. These A, Bs, and Cs and so on, that represents the input of a control pulse to each of the routers, because what needs to happen is based on the packet's destination and based on the router's existing location, the router has to decide where to send the packet, up or down in this butterfly. So, and that A, B, and C is basically telling the router where it is in the network so it can make that decision. That's the idea behind it. So here we build a 4x4, and here we build an 8x8 using a mesh. These shift registers, again, are delay elements. They delay the packet by what it needs to delay to enter the next router, the next epoch. So this has to do with some of the timing we alluded to. I can answer some of those questions if you'd like, but this is just there to make the notion work of race logic, because otherwise what would happen is at every hop, the control pass will get delayed by a bit, and eventually the destination would change. So that's what we're trying to avoid here. And we can, so this one of the selling points of this network is, again, area efficiency, like the whole thing with I've been talking about all this time. And depending on the packet length, we can get up to 5x higher throughput per JJ, but that's for long packets. Short packets, what happens is that the payload is smaller compared to the control part, to the header of the packet. Again, I can go into more detail. Okay, so what's next? We want to move to lower temperatures, and we want to look at some of the challenges at lower temperatures. Some of the challenges at lower temperatures, of course, one of the first ones we can think of, and you can see that in the slide, is the power ceiling. So we go, for example, at 4 Kelvin, we're talking about milliwatts that the circuit can dissipate. That can become microwatts. And I'm only giving you an order of magnitude because, yes, it does depend, of course. But we have a much lower power ceiling because of the cooling constraints at lower temperatures. And in the very simplistic case, what we did here, just to show you, the distance between achieving that goal, if we take a 16-bit adder, take it through QPalace, this is version 1, and then, just assume 50% activity factor in every input, which is, the simplistic assumption that these and other tools make to give you power without simulation. So we have 10 milliwatts of active power just for this adder. So it's a big gap if our target is microwatts. There are things we can do. We can make the circuit smaller. We can lower the activity factor because 50% is high, but still it's not enough to cover. We can lower the clock frequency. We can use ERSFQ and so on to reduce the static power consumption, which is a big part in RSFQ. And sure, to some degree that can work, but still 1000x approximately is a big gap. But if we look at USFQ, this comes from, USFQ, the unary compute, if we just look at the dot product unit, as well as balancer, which is basically the counting network that I mentioned that adds everything, and then the multiplier, the active power is much, much lower. It's like it's already to the order of microwatts. So this is good. That means that if we can express our computational performance with USFQ, at least at the order of magnitude level, at a high level, we can, it's possible, quite possible to meet the cooling requirements, the power dissipation requirements at these lower temperatures of the millikelvin. And something that we're looking into more recently is some of these sensors operate at, what DOE recently started calling a couple of years ago in FOAs, or at least that's when I saw it. Maybe it happened before. Harsh environments. And harsh environments can be circuits that are affected by strong magnetic fields that come from the outside. Could be radiation as well, or it could be thermal noise, or it could be imperfections. But for whatever reason, all these factors can add uncertainty and bit errors inside the circuit. And that is an interesting thing to note about, because it's not just area efficiency. It's reliability does get affected by the compute logic. As one example, let's compare binary pulse trains and race logic when it comes to bit error rate. So if you look at binary, for example, if I have a binary representation, and I'm showing it top to bottom here, like a parallel set of wires. If a pulse appears that shouldn't be there, the error in the numerical error can be as high as half of the maximum range, depending on like if it's in the most significant position, and anywhere in between, depending on the position. So there's a lot of uncertainty. Going back to the multiplication example we saw with USFQ, if we look at a pulse train operand, if a pulse appears where it shouldn't be, the error is both small and predictable, and that is a good quality. So if a pulse shifts, I didn't mention that, so there's also the timing uncertainty. So say now that there's more of a jitter than we thought. If a pulse shifts and appears at a different time slot, there's no numerical effect in terms of error. Now, if it collides with another pulse that was there, it might. But in that case, it sort of becomes like the second case, which is a pulse appears or disappears, where in this case, it's a small and bounded error. So basically, what's the value, the numerical value of one pulse, which is small. But then if we look at race logic, a pulse shift has a small numerical error. A pulse disappearing entirely is a bad case, because now the value becomes 0. And a pulse appearing out of nowhere can have either no numerical error or can reduce the value of it can reduce the numerical value of this race logic operand. So there's still some bad cases, of course, but there's also good cases. And actually, let me go back. And remember the graph that I showed you earlier with the cables that have bandwidths of 1, 1.5, and 2 gigabits per second, but at higher bandwidths, now we have a higher bit error rate. Well, if we can manage to make our data transport with, as an example, a pulse train representation, now we can probably operate at this higher bit error rate, because the numerical effect of the errors will be small, and they're bounded and predictable, which is really useful. But by accepting that small trade-off, now we can operate at twice the bandwidth, for example, which can be a big win. And then when it comes to the combining that with race logic, yeah, there's still bad cases, but there's also many good cases. So we'll see how that would average out in any particular applications. Okay, so I think that's more or less all the time I had. I talked about how compute models affect efficiency and reliability. This is also some work we have going on. This is a small project when we're trying to figure out how reliable an ATC is, superconducting, and that's ongoing work. And a lot of the stuff that I talked about is already here. So, but what we are designing matters a lot. I did focus on cryosensors, but a lot of what I talked about also applies to if we take an HPC application kernel, for example, and try to put it on a superconducting chip. Okay, and I think I can pause here for more questions if there are any.
Well, thank you very much.
Thank you.
It was very interesting. And the talk is open for questions.
I have a question.
Go ahead.
Yes.
Hello. So how do you interface this race or temporal logic with the standard CMOS electronics? Like, say you want to send it to room temperature or the memory. How that interface looks like?
So there's the binary. Okay, so there's the interface with binary, and there's the interface with room temperature. And the interface with room temperature, we sort of piggyback on cabling technologies that are already out there. On the input side, for example, there are DC to SFQ converters, and there's SFQ to DC converters out to the cable, and then on the other side, it lands on similar circuits, but on room temperature CMOS. And then when it comes to binary to race logic and vice versa, we've designed circuits that I didn't show here that basically at the high level you can think of it as counters, for example. And I can send you some paper. I don't have any diagrams here in this but basically the idea of them is like, here's a binary value. Okay, you can use it as a countdown value and then produce a race logic pulse. That's on one side you do it, but we avoid it because the moment you do that, the conversion is not too complicated, but it's also not cheap. And of course, yeah, so we avoid it as much as possible. When it comes to memory, race logic memory has some challenges too, but there's also some interesting work from UCSB, now Wisconsin, that relate to that as well. So we can, we're slowly building up an ecosystem with. So they build memory that you can also store temporal values in. For example, we built a cell that you can do this for with like just few wires.
Mhm.
Yeah, maybe that was a convoluted answer, but anyway, it's the point is that there are conversions, but we try to avoid them.
So like just to understand, if I understand correctly, you do the conversion, say from unary to binary, and then it send it to the room temperature, right? And
Yes, that could be one way of doing it. Yeah, and that could
okay.
be a good way of doing it, because the moment you do this at the very end, you only do it once, and then you can apply, for example, error correction codes, because those cables have bit arrays. But what I was talking, sort of alluding to here, is that you could do the sort of the opposite. You can transport numbers of events through the cable to room temperature. So basically transport these pulse trains. They're not going to be pulsers. They're going to be like individual bits, sort of, but the same idea. And that's if we want to accept errors, but bound their impact, and then do the conversion in room temperature, because there the conversion is even cheaper. We haven't done the comparison. We sort of, run out of money a long time ago, but yeah.
Okay. Yeah. Thank you.
Yeah.
Okay. Some other questions? I'm kind of curious to what extent your concept kind of overlaps with ideas of optical computing, where people also use pulses.
Yeah, there are some common concepts. It's just the building blocks. I'm not an expert, but from what I know with photonic computing, the building blocks change, like the cells, the logic gates that we build with. But there's also good work with optical computing that tries to do this, multiply add. I think there are a bunch of papers, but we haven't really done a comparison, because it's not. At a high level, sure, but it's not exactly apples to apples. Not exactly, but yeah.
I agree,
Yeah.
but it's that general concept of time bins and using pulses to encode information.
Yeah, at a high level, there are definitely similarities. The building blocks differ, but at a high level, yeah.
Yeah. Okay.